All right, so let's practice this idea, this theory on a problem. So we have the function 1 over n natural log of n. So the first thing I'm going to do, I'm going to graph that function that matches this and see if it satisfies our conditions. Because if it doesn't satisfy our conditions, we've got problems. So let me pull up Desmos really quickly. Oh, wrong one. Oh, that is not what you need at all. Hold on, I'm in the wrong area. There we go. Okay, so let me pull up another Desmos. We don't need that, and we don't need that. Okay, so I want to graph 1 over x natural log of x, right? Because I want the function to match the series, or excuse me, the sequence that's inside the series. So I'm going to let f of x equal 1 divided by x natural log of x, like that. And again, I don't really care what it's doing over here. That's kind of irrelevant, especially if you look at the series, because the series starts at 2. Mm-hmm. So I'm actually only going to look at this graph for x greater than or equal to 2. And I don't really care about the rest of it. Let me zoom in. Isn't that lovely? Beautiful, marvelous. There, I changed the scale just a little bit. And then I'm going to draw this picture on my page to show that I'm paying attention to my requirements. Let me pull this out. So I'm going to grab it over here. And I'm going to graph, let's see, 1, 2, because I don't really care about the beginning part. 3, 4, 5, 6, 7. This is going to 1. This was going to, it's basically 0 and 0. And then it went, let's see. So from 2 at about 0.8, and it swooped downward. And that's what I'm going to graph. Okay, so this is f of x equals 1 over x natural log of x. Now you'll notice it is positive, it is continuous, and it is decreasing. Check, check, check. We have all 3 of our conditions. So we do that graph first to show that we know what we're doing, right? We have to check that this works. Otherwise, the integral test fails. So the integral test has requirements. Oh, I went away from them. The integral test has requirements that we have to meet. It has to be continuous, positive, and decreasing, and we have to show that we've met those requirements. And we have. Oh, my graph is being weird. Sorry. There we go. Sorry about that. My window got strange. Okay, so now I want to find that integral. So I want to, oh, here we go. I want to find the integral. So I'm going to find the integral from 2 to infinity of 1 over x natural log of x. But we learned in chapter 8, I think it was chapter 8, that we have to take the limit as, it doesn't matter what letter you pick, I'll do b. b goes to infinity, 2 to b of 1 over x natural log of x dx. And again, that was section 8.9, I believe. It's the one with infinite integrals that we learned. And then that's a u substitution. That's u because du is 1 over x dx. Therefore, this is equal to the limit as b goes to infinity of, and then it'd be the integral of 1 over u du. Right? I'm not going to bother with values. So technically this is u of 2 and this is u of b, right, if you wanted to be technical about it. Right? Because I'm going to back substitute in a minute anyway. But the integral of 1 over u, that's natural log of the absolute value of u. Ooh, but I'm still taking the limit, sorry. The limit is b goes to infinity of the natural log of the absolute value of u, right? And again, that's from our two values, so we're not going to bother with that. So that equals the limit as b goes to infinity of the natural log of the absolute value of, and u was the natural log of x. And we're going to take that from 2 to b. So I'm putting 2 and b back in here. Technically, this one is from u of 2 and u of b, but I didn't bother. So I just waited and put back in the values, right? And then, right, that natural log of x goes right there, so 2 to b. And if you want to ignore the u of 2 and u of b and not put them in and just leave them blank, that's fine. Leaving them blank is better than actually putting in 2 and b, because 2 and b is not correct in these two spots. But it is correct back here because I went and back substituted in what the natural log of x was. All right, so then this is equal to the limit as b goes to infinity of the natural log of the natural log of b, I guess I can just do it that way, minus the natural log of the natural log of 2. There we go. My b is so strange. It looks like a 6, and it's not a 6. It's a b. I'm sorry. All right, then let's think about this for a second. You're taking the limit as this thing as it goes to infinity. This sucker goes to infinity, right? So the natural log of infinity is infinity, and the natural log of that infinity is also infinity. So this sucker's infinity. And this is just some constant. Who cares? But if you take infinity minus whatever the heck this is, you know what you got? You've got infinity, right? So this is infinity, right? So this is some number. Well, it's the natural log of the natural log of 2, whatever the heck that is. So it's a constant. And if you have infinity minus a constant, you have infinity. We've learned that a long time ago. Therefore, the integral diverges. So we're taking the concepts that we learned for those infinite integrals, and now we're putting them to good use with these series. Since the integral diverges, and this integral and that series are well, let me put it this way. This is the function that builds this sequence, right? In other words, this sequence in here is this function for integer values of n, right? They are one and the same, essentially. Therefore, the series, sorry, that was a weird triangle. Therefore, the series from n equals 2 to infinity of 1 over n natural log of n diverges also. If the integral diverges, the series diverges, right? The series that is built from that function. Now let's repeat the process for this value, or this function. So, well, it's a series at this point, but I'm going to make it a function. So my function would be x times e to the negative x squared, right? I'm taking the series and I'm building it into a function. And as before, we don't really need nearly as much as we are seeing here. And you can see that the beginning part, like I said, there are a lot of functions that go up, but then they come back down like a roller coaster. But they're not going to go back up, right? So it's okay that this part over here on the left is, let me bring it out, that this part over here is going up, but it doesn't really matter. What we care about is this part over here on the right. What we care about is this section of the graph continuous, positive, and decreasing? And the answer is yes to all of those. This part does not matter. That's that part from the integral test from before, right? It doesn't matter if it's doing something weird at the beginning, as long as it's decreasing and positive in the long run, which this is, then we're fine. All right, so then I'm going to make an equivalent, not equivalent, sorry, these are not equivalent, but we are going to find the integral. I'm going to take this series, or excuse me, this sequence, right, this from the series. So here the series is the overall thing with the sum. The sequence is this part in it, and I made a function of it. What was that function? that I graphed over here. It was f of x equals x times e to the negative x squared, right? So that's what I'm going to do. I'm going to find the integral from 0 to infinity of x e to the negative x squared. Okay, but we learned in section 8.9 that we don't write them like that. We write them as the limit as b goes to infinity. And it doesn't have to be b. It can be pretty much any letter you like other than x. So of the integral 0 to b x e to the negative x squared. Okay, so hello u substitution. U is negative x squared. Du equals negative 2x dx. Oh, I forgot my dx. Bad. There it is. Okay, so I don't want the negative 2 part of that. I want negative 1/2 du, which is x dx, because x dx is what is in my problem. Okay, so then what I'm going to do is I'm going to take the limit as b goes to infinity of the integral of e to the u, and then I'm going to have a negative 1/2 out here du. And I'm going to leave these blank. They're technically function values of the b, but I'm not even going to deal with it. Just remember, you can't put in 0 and infinity. That would be bad, right? So, but we're just going to kind of leave them. We can't put in 0 and b either. Those aren't correct either. You just have to wait. So, because it's actually not even 0 down here, it's something else. So then we are going to integrate that, but we all know the integral of e to the u is e to the u. So it's the limit as b goes to infinity of negative 1/2. The integral of e to the u is e to the u. I won't worry about the plus c because technically there's two values here. Technically it's u of 0 and u of b if you really want to know. All right, and then that would be the limit as b goes to infinity of negative 1/2. Sorry, I'll keep the color coding up for just a little bit longer. Negative 1/2 e to the negative x squared. And now I can put in the values. So now I can say what I wanted to take those for, those x values. The x values are 0 and b. Okay. So this is u of 0 here. This is u of b over here. Okay, so now I'm going to put in 0 and b, and I'm going to take the limit. So that would be negative 1/2 e to the negative b squared minus a negative 1/2 e to the negative 0 squared. Weird. Okay, well, oh, and I'm taking the limit as b goes to infinity of all of this. Okay, so that's the limit as b goes to infinity of, well, a negative power is really putting that value in the denominator. So I'm going to rewrite this. It's negative 1 over 2e to the b squared minus a 1/2, right? Because this part right here, e to the 0 squared is 1, right? And minus a minus is plus. So 1/2 times 1 is 1/2. So this is really plus 1/2. Okay, so I'm going to take infinity. Let's think about this for a second. I'm going to take infinity. I'm going to put it in there. What's that going to be? Well, that's going to be negative 1 over 2 times e to the infinity. E to the infinity is infinity. And then 2 times infinity is infinity. So this whole thing is negative 1 over infinity, right? So let me rewrite that. So this is negative 1 over infinity plus 1/2. Well, negative 1 over infinity is 0. So this is 0 plus 1/2, which is 1/2. Whereas the one above was infinity. So that one diverged. This one is 1/2. Ah, so the integral converges to 1/2. So the integral converges to 1/2. Therefore, the series from 0 to infinity of n e to the negative n squared converges. It does not go to 1/2, right? The integral goes to 1/2, The series does not. But we know the series must converge because they go together. That's what the integral test says. They're going to go together, either converge together or diverge together, but they're not going to converge to the same value. Divergent is easy because divergence is infinity everywhere. All right. But even though this converges, it's not converging to infinity, but not to 1/2, right? 1/2 is the integral part, but it's not the series. Let me just remind you, right? The integral part is a picture. So we know that this area, for example, is a half. Even it's not that area, it's the area to infinity. So imagine this area goes to infinity, we know that it's a half. But the series is not going to be a half because the series is either an overestimate or an underestimate depending on how it's built, right? So it is not going to be a half, right? But we do know it is going to converge.